How many of you read my announcement from last night? Good. Good handful of you. If you haven't, take a look at it. I wanted to get that posted on Friday. And I had to sub for a lab whose instructor had to leave. Can't actually take the lab this semester. So we were kind of scrambling, and that consumed my Friday afternoon. So I plan on posting those more towards the end of the week so that you have those weekly updates going into the weekend when I know that a lot of you have scheduled a lot of study time using that Unit 0, use AI to make a study plan. You broke the AI? Well, good for you. I didn't know you could do that. So I'm going to try to post those weekly updates on Fridays so that you guys have them. But take a look at it because it will be useful. Now, to be fair, I kind of feel like we have just finished the first week of class despite having gone through 2 weeks of the semester. And I think I told you guys this already, but the other sections have a slightly different schedule. They've met 4 times already. They've met twice as many times as we have. So a lot of them are finishing up Unit 1 and Unit 2 already, and they're planning on taking their first unit test this weekend. Which is important because the unit test is your first major assignment, and it tells you what you should expect to put into this course. And for those sections that are taking the unit test this weekend, they'll actually have their results back before next Tuesday, which if this loads, you'll see that next Tuesday is the last day to drop a course. Now, I hope none of you have to drop. I hope you can all stay this semester. But I know that realistically, there are some of you that are saying, I'm just here because I might need this and I don't know. I'm here because I needed a certain number of credits, but I'm willing to drop some credits too. So if you are someone that is riding the fence about this class and you want to know whether you should stick it out with me this semester or schedule it in for a different semester, then definitely plan on taking one of the practice unit tests this weekend so that you get a feel for what it's going to be like. And if you really, really want to take a real unit test, you're going to have to try and finish all of Unit 2, which we're going to finish by next Monday. You're going to have to try and finish all of Unit 2 and be ready to take a unit test this weekend. So if you're not worried about this class and you know that I'm here to support you as best as I can, then we're on pace to take our first unit test at the end of next week, while other sections are on pace to finish it this week. Does that make sense, Daniel? Let's double check. I don't know if you guys know how to do this, but you can just search. I have this pinned actually. You can search for the Slick School Calendar. I'll take this link to fall 2025. And here's September 16th, last day to drop classes with a 100% refund, and it doesn't show up on your transcript. After the 16th, it's on your transcript forever, whether it's a letter grade or a W, and you can't get your money back. And I talked to you guys about that registration appeal process, which is just a weird situation. So, does that clear it up, Daniel? Are you agree now? Okay, good. I'm glad that you pushed on that because I have been wrong before, and I'm always happy to double check it. So we feel a little bit slow getting into this semester, right? I had actually hoped that we would wrap up Module 1 last week, but I wanted to take that time to get to know you guys and have you guys share about yourselves in class. So we're going to finish up Module 1 today. Maybe we'll make it to the end of Module 2. That is the end of Unit 1 in RealChem, Section 1 on Canvas, which means that by Wednesday's lecture, you should start preparing for Module 3. You should skim and scan Module 3. You should take the pre-reading quiz for Module 3. You should be prepared to be moving into Unit 2. We may have to wrap up parts of Module 2 on Wednesday, but I think we've got a good chance of getting into Unit 2 on Wednesday. Don't want you guys to feel confused because I know the calendar feels all out of sorts. I tried to shift things in the calendar, but there are a lot of things on that calendar, and I know that can feel really confusing. I hope that you can at least see this as the big picture of where we are in the class. Yeah? And always feel free to shoot me messages when you've got questions. Okay. So, if you got funny little memes or chemistry stories you want me to put on the board, I won't necessarily say who sent them in unless you want me to. But I'm happy to start class that way. Like I said, I'm kind of bad at that stuff. But I love the examples that you guys find. I think they're really good. Okay. Last week, when we were working together at Module 1, we decided that we should describe things with their physical properties and their chemical properties. And then we talked a little bit about those physical properties, predominantly the phase of matter. So I want to take a quick review with you guys. If this is a phase diagram, without looking at your notes, think of this as kind of a Feynman technique exercise. Without looking at your notes, can you tell me which axis is pressure and which one is temperature? Remind me your name? Berkeley, thank you. Pressure, temperature. Anybody disagree? How do you remember that? Memorized it? Now, I will say it's arbitrary. It doesn't actually mean anything. Which one is pressure, which one is temperature? It does change the shape of the graph. And what I remember when I was a chemistry student, even today, what I remember is the shape of those lines in the phase diagram. Do you guys remember what I said last week it looks like? Kind of this curvy Y. So this is what I remember. And then I try to fill in all of the conditions. So I know that high pressure and low temperature gives me a solid, and that's about the point where I feel confident that this must be pressure and this must be temperature. Maybe that feels a bit arbitrary, but luckily you won't have to guess which is pressure, which is temperature, but I do want you to recognize that you've looked at it enough times. You should try and pay attention to what is where. Now remind me, low pressure, high temperature, what phase do we have? Gas. And then right in the middle, our liquid. So let's take an example. Let's say that this, I'll use a different color here. Let's say that this line here represents 1 atmosphere. That is normal pressure. That's basically what we're experiencing right now. But because we're not at 18th century Paris, France's elevation, we actually have a little bit of a lower pressure, a little bit less than 1 atmosphere. Can you tell me what temperature is right here in degrees Celsius? Right? Oh, I didn't give you what chemical we're looking at, did I? Assuming we're looking at water. If this is water's phase diagram, what temperature do we see? 0 degrees C. How does Ryan know that? Because, sorry, go ahead.
Because it's right in the middle of a solid and a liquid. So you would assume it's like freezing?
We're looking at the transition state, the phase transition between solid and liquid. So that is the freezing or melting point. depending on how your temperature or pressure is going. And because we know water well enough, we know that water freezes and melts at 0 degrees C. Can you tell me what I would need to do to my pressure to take solid water and transition it not into liquid water, but transition it directly into a gas? That's a process called sublimation. I would need to lower the atmosphere, bring the earth closer to me, bring the sky closer. Could I bring the temperature up? Stay at the same pressure, but bring the temperature up? I don't think I actually will. At this pressure, I will eventually go from liquid into gas if my line went high enough. But at that same pressure, I'll never go from solid to gas. Lower my pressure. If I stay at the same pressure and I change my temperature, I'll never sublime. But I need to lower my pressure. Right about here is something that we call the triple point. That is a temperature and pressure ratio at which all three states of matter exist at the same time. It's not a solid inherently, it's not a liquid inherently, it's not a gas. It has all of those properties. I need to drop my pressure below this point so that I can transition directly from a solid to a gas. So I need to lower my pressure in order to allow my liquid water to sublime. And how does the temperature of sublimation at that lower pressure relate to the temperature of melting, which we looked at before? Now I feel like I'm being a little bit vague here. At 1 atmosphere, I went through a phase change at 0 degrees C from solid to liquid. Now I'm lowering to less than 1 atmosphere, and I want to know at what temperature I see a phase change from solid to gas. How does that temperature relate to the temperature of melting?
Would it be 100 degrees at that?
No, and I don't want you to think I'm trying to trick you. Actually, I think it maybe seems a little too obvious. I don't think so. Looking at this graph, the temperature for the phase change of sublimation at this new pressure does not look the same as the temperature of phase change before. Yeah, I couldn't have you give me an actual number. Maybe that's what felt hard. But it will be colder. It will happen at a colder temperature. So right here is the new phase change from solid to gas at this arbitrary pressure. So I have said that this is simply less than 1 atmosphere. And so all I really know is that this is less than 0 degrees C. So if you want to take your solid ice and you want to turn it directly into a gas, you don't want it to melt and then boil, you're going to lower the pressure, you're going to suck out the air from around your ice. You'll notice that the temperature at which it transitions is actually colder than the freezing point of liquid water, which might feel weird, but you have changed more than one variable. You've changed the pressure. So now temperature is impacted by that as well. This is the usefulness of a phase diagram. What is going to happen to my substance when I change temperature and when I change pressure? Okay? All right. Let's keep moving. Up next is talking a bit about chemical changes. How can we define a chemical change? When something heats up or cools down, is that a chemical change? When something changes state, is that a chemical change? Changing state is not a chemical change inherently if it stays the same. So that a chemical change is the result of. A chemical reaction. I'm underlining reaction there because throughout the semester we'll be talking a lot about reactions, and we should abbreviate it at some point. So RXN to abbreviate reaction. So I can tell rubbing alcohol apart from water because they have different boiling points. That would be a physical difference between them. Our chemical difference is whether or not a chemical will change in a reaction. So, for instance, isopropyl alcohol, rubbing alcohol, burns. I can light rubbing alcohol on fire. Water does not burn. Chemical difference between the two. An important concept in our chemical reactions, our chemical changes, is the law of conservation of mass, or the law of conservation of matter. Someone that's being introduced to chemistry for the first time might say that as I burn my rubbing alcohol, it's gone. I don't know where it is. But I cannot destroy that mass. I can't say that mass is just transformed into energy. It's being conserved in some way. Matter cannot be created or destroyed. It only what? It only transforms. It only changes. So what does it change into? How can we show this? We show this transformation by chemical equations. Now, to be fair, sometimes you can show an equation that gives you a physical change. It's just not super common. I'll give you guys both. Chemical equations are going to have starting material on the left, things that it transforms into on the right, and they'll be separated by an arrow. That arrow represents basically an equal sign in a mathematical equation. So if I take carbon dioxide in a gas state, so I'm putting subscript parentheses G, and I take water in a liquid state, then I can transform it into solid sugar and elemental oxygen. And I actually didn't mean to put these as chemical formulas. I meant to actually write them out. Whichever one makes the most sense to you, that's okay. For right now, it's just an example of showing the transformation of matter. Carbon dioxide is matter. Water is matter. Together, they can be transformed into sugar, which is matter, and oxygen, which is matter. Okay, can you tell me whether this is a chemical change or a physical change?
Chemical.
Why?
Because you combine two different elements and then they turn into something new.
Now, if I had not put the chemical formulas. If I had only put words, could you say elements, or should we pick a different term?
I would say compound.
Compound, substance, chemical, right? One or more chemicals change, become a different type of chemical. Okay, how about this example? Carbon dioxide solid becomes carbon dioxide gas. If you guys have ever had dry ice, that's what this is. It's that chunk of carbon dioxide subliming into a vapor. Physical change or chemical change? Physical change. Because no chemical has actually changed. Only a physical property. Type of matter is unchanged. But notice how we can use that equal sign, that arrow, to say there is no lost matter. It's just changing in some way. All right. Now, this is a really fun conversation for me to have. I think I can get a little bit lost in the weeds on it, so try to rein me in if it feels like I'm going too far. But the conversation about scale in chemistry is very cool. In fact, I mentioned that in November I'll be giving a talk, part of a STEM Fun Talk series, and I'm basically talking about the scale of energy from atomic and molecular energy all the way up to larger forms in the universe. And so this is a really cool idea to me, the scale of energy. Can you try to define what scale means or its usefulness? You know what it means. Good. How something relates to something else in size. Anybody want to add to that?
Maybe like range, like the electromagnetic scale kind of has a range of different wavelengths.
A range, yeah. Am I looking at this frequency of electromagnetic radiation, or am I looking at this frequency? Because it's all put out on a range, and so I've got things that I can scale up or scale down.
A measurement.
A measurement, sure. Scales are things that you weigh things on, right? Like a balance can be called a scale. So in a way, you are measuring something in relation to something else, right? Because you've got to have a unit. The distance between observer and object could be a scale. Yeah? Okay? These are all good things. So let's try to rein it in. I think all of these give us different perspectives. And I think we can sum it up by saying how large something is relative to something else. So in other words, scale is some sort of comparison. So with Alina's example, maybe between me and the moon, there's a huge distance, but between me and my desk, there's a small difference. So the scale of distance between those two things, quite drastic. If you get hit with gamma wave radiation versus being hit with radio wave radiation, the scale of that energy is quite different. Gamma ray turns you into the Hulk. Radio wave just passes right through you. Oh, I watched a creepy thing. You can use your brain. I don't know if I recommend doing this. I haven't seen the science behind it, but you can use your brain or your body or a water bottle, because your body is mostly water, as an antenna for your remote control on your car. So this girl put her remote up to her head and unlocked her car, which was too far away to be unlocked otherwise. You tried it? I watched her do it.
I've
So
done it a million times, just right up to the bottom of my chest.
you've done it.
Like growing up, my dad always did it. And
Maybe you guys need to try to find your scale better.
I've had it work.
Crazy. I'm not trying it, to be honest.
I feel like it was, I don't know, I'm like, my dad always did it growing up, and I never just like thought, like, maybe it was not great for me.
Wow. I will say, you probably have a bigger risk from all the electronic devices in here than you do from once a day clicking your remote to your head. But again, the scale between gamma rays and radio waves, so large that radio waves, not really damaging to you. Gamma rays will eat right through you. All right. Well, because we look at some things that are so large and some things that are so small, we will use scientific notation to help bring the scale down. One of the best uses of scientific notation. It makes very big and very small things measurements, like Edgar said. Easy to read. Because you guys have seen zeros after zeros after zeros after zeros, and then you go for the commas and you start counting how many commas you see, adding up in your head, 1,000, million, billion, trillion, quadrillion. Okay, I lost track after some point and I don't know the numbers anymore. Scientific notation just compresses all of that and gives us less numbers to look at so we can still understand the scale. So here's a few things for us to put onto a scale. The gold atom, the size of an atom of gold, up to the Earth's diameter, and in the middle I'm putting your face. We do need a unit for this measurement. So we're measuring length in each of these three instances, and the scientific agreed upon the international unit of length. You guys know? Meters. Great. So, in terms of scale, which of these measurements is the most relatable to you? Something that's not very large or very small?
My face.
I hope so. And your face is about 10 to the minus 1 meters. That is, your face is about 0.1 meters long. I actually don't remember if I measured tall or wide, but regardless, less than a meter. The gold atom is about 10 to the minus 10 meters wide. If I were to write that without scientific notation, I would need to have this 1 precede, or excuse me, I guess, yeah, it's about 1 times 10 to the negative 10. So I'd have this 1 preceded by moving the decimal to the left 10 times, which means it actually has how many zeros? 9 zeros. So when you've got that negative exponent, you've always got 1 less than that, zeros, in front of your first digit. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0.0. I do want to point out another thing. I do this weird thing where my first 0, it usually has a slash through it. Sometimes I do that to just designate that it's a 0 and not get confused with anything else. You don't have to do it, it's just what I do. So that's a very small number, and it's kind of hard to read. I know that it's a lot smaller than my face because my face is about this big, but how much smaller is it? I don't know. And what about the size of the Earth, the Earth's diameter? Do you guys have a guess in scientific notation? It's not 10 to the positive 10, no. It'll be a little bit smaller. Yeah, 10 to the 7th meters. So if we're saying 1 times 10 to the 7, then we're saying 1 followed by how many zeros? No, 7. It is weird. But if I've got 1 times 10 to the 7, I've got 1 decimal point. And then I move that decimal point to the right 7 times, so that creates 7 zeros. So when your exponent is negative, you've got 1 less than that number of zeros before it. When your exponent is positive, you move your decimal to the right that many times. So if there is no other number, then it's that many zeros. So here's 7 zeros. You guys tell me, 10 to the negative 10, 10 to the negative 1, 10 to the 7. Does that put scale on an, does it make it easier for you to comprehend? Or is this easier for you to comprehend? Scientific notation or standard notation? Anybody disagree? Standard notation scratches an itch better that tells you what it is? Okay, that's fair. Then live in that discomfort, right? Get used to it because it's not going away. And you can bridge that gap. You can say, that number makes sense to me, so now when I see this, visually in my head, I will imagine that. 9 zeros in front. Cool. Okay, I love scale. For instance, did you know that there are more atoms of hydrogen in a molecule of water than there are stars in our solar system? All right, I'm going to say that one more time. There are more atoms of hydrogen in a molecule of water. So that's H2O, which has how many atoms of hydrogen? 2. Then there are stars in our solar system. How many stars in our solar system? Our solar system. Our solar system. Not our galaxy. Just 1. See how the scale of talking about small and big things threw you off? But if I had given you the numbers there, 2 atoms of hydrogen in a molecule of water, 1 star in our solar system, the sun. Now, there are more molecules of water in a cup of water than there are stars in our galaxy. There are about 100 billion stars in our galaxy. So we can write that as let's write it out. 100 billion. Not the easiest number to write. So I'm going to write this as 1 times 10 to what power? 8? So here's the deal. I want to take my decimal point, which is here at the moment, and I want to bring that decimal point so that my number is no smaller than 1, no larger than 10. 10 actually is too much. So between 1 and 10. So I'm going to move this decimal point to the left. 1, 2, 3, 4, 5, 6, 7, 8. That's how many stars there are in the Milky Way galaxy, roughly. And if you have a cup of water, here's how many molecules of water are in that cup. 6 times 10 to the 23rd. It's not even comparable how many molecules of water are in a single glass of water when you compare it to how many stars are in our solar system. That's scale. There's actually so many more small things than there are big things. All right, good talk? Great. Before we get into Module 2, Module 1 kind of wraps up in a weird way. So I just want to make sure that we're on the same page in case you haven't done your Module 1 checkpoint yet. I want you to feel capable of doing that. So first, a discussion on purity. Specifically, purity at different scales. Purity at our macro scale, purity at the scale of a planet, purity at the scale of a atom or a molecule. Homogeneous describes something that is uniform throughout. I think that if you looked at salt water, you would say it looks homogeneous, right? It looks uniform. You don't see the salt that's dissolved. All you see is that clear liquid. But then you zoom in, not from your scale of 10 to the minus 1 meters, but to the scale of an atom, 10 to the minus 10 meters, and now you see molecules of water with sodium plus ions and chloride minus ions floating throughout. It doesn't look homogeneous anymore. Now it looks heterogeneous. Is ununiform too many UNs in a row? You could say variable in composition as well. So this is another example of us as humans trying to create nice little definitions and draw these lines in the sand and then fit nature inside of it. So we'd like to say this is homogeneous and this is not homogeneous. But then we zoom into a different scale and suddenly it starts to look homogeneous or non-homogeneous, right? So look at milk, it looks homogeneous. You zoom in, you find out that there's fats, there's protein, and there's water. It's not homogeneous. You look at the ocean and you see the coral, the fish, the sharks, and then you zoom out and you don't see the coral or the fish or the sharks, and it's just water and it looks homogeneous. So purity is a bit arbitrary. It matters what scale you're looking at. That's the point here. These can vary at scale. Okay, a quick discussion on the building blocks of these chemicals. Atoms are individual units of matter. It's not quite true. It's not really our smallest unit of matter, because matter is things with mass that take up space. And we're going to say that atoms can actually be broken down too. But in our context of chemistry, we're looking predominantly at the atoms that things are made up of. So this is good. We'll understand how atoms are made up of those smaller units, but atom is our main unit. These are differentiated by their element type. mentioned earlier, water, 2 H's, 1 O. That H is an element. O is an element. All of these different elements, where do you find them? Where are they housed? Throughout the universe. That's true. Yeah, I don't think I phrased that very well. You'll find these on our periodic table. The periodic table of elements. And we'll talk about why it's called the periodic table and not just a table of elements, because it actually gives us useful information about how these elements relate to one another. It's not just a cluster of different units of matter. These are identified by their chemical symbols. We've already used chemical symbols. I'm about to erase some chemical symbols on the board. I know some of you have already had a lot of chemistry experience, others not. So can you tell me some chemical symbols? H. Ryan gave me H. Edgar? Good. H, He, Be. What is Au? What is Ag? Silver. Gold and silver. Good. O2 is not a chemical symbol inherently because it has that number in it as well. O2 is a chemical formula.
I only said O2 because I was watching a video and the lecturer was saying that certain chemicals come as a bundle.
That's right. So we would say O2 is elemental oxygen, even though it's not one element. So take away the number and you've got a symbol, which is, good job, Brian, O. And we'll talk about O2 as a molecule and as an element. O3 is also elemental oxygen. That is a natural way that oxygen is found. But you won't ever find oxygen as just a single atom of O. Other chemical symbols that you guys know and love. Fe for iron. Nice. What else? Argon, copper, xenon. Sorry? Einsteinium. I actually would have to double check that. It's buried down there. It's one of those elements that is like synthesized in a lab and exists for a millisecond. So true. Mg. You know that one? Magnesium. Now you guys you've said so many, but there's one that literally makes up C. Right, of course. The organic chemistry professor wants you to talk about carbon. But there is good reason to believe you wouldn't exist without that element. But luckily, a lot of stars produce carbon. Carbon is one of the most abundant elements in the universe. So there's a good chance that you would have come around to existing. All right, that's how we represent our elements. We use these chemical symbols. Then we talk about chemical formulas and names. Chemical formulas and names. These follow IUPAC rules. Do you know what IUPAC stands for? Can you guess what IUPAC stands for? Yes, international. Not unit. Union of, there's an O in there that's invisible. Pure. And, the A stands for and. Oh, no, it doesn't. And then A. International Union of Pure and Applied Chemistry. You guys were not close at all. Good job. Good effort, though. So the International Union of Pure and Applied Chemistry, talk about putting yourself on a high horse. They are the ones that develop all of the rules. When you have a chemical symbol, or excuse me, a chemical formula, you write the symbols in a specific sequence according to IUPAC. When you name that chemical, you use prefixes, suffixes, and you change the element name in specific ways according to IUPAC rules. So we'll be learning about nomenclature, systems of naming, and we'll be following IUPAC rules. Personally, I love IUPAC because it standardizes communication about chemicals, which is a very challenging thing to do. And I actually believe they could do better, but at least somebody is out there trying to standardize it. Most people, we even have a sign upstairs in our club room, the chemistry club room, that says, I hate IUPAC. And I don't agree with it, but a lot of people struggle because it feels like they're having rules forced on them. All right. Now we said that these were all things about atoms. Atoms are different elements. You find them on the periodic table. They've each got their chemical symbol. And then when atoms come together, they get these formulas and names. But one of the other building blocks that will be important to us is not just atoms in general, but molecules or compounds. And we're going to talk a little bit more later about what these are, but molecules have at least 2 atoms. Compounds have at least 2 types of elements. So they are a Venn diagram that overlap a little bit. 2 or more atoms. And these molecules or compounds, they exist because they're held together. They're held together by chemical bonds. I don't know, if you were to ask me, this feels a little bit like a snake eating its tail. Chemicals are made up of elements, and those elements are held together by chemical bonds. So what does chemical mean? It's just what exists on the scale of the elements, on the scale of atoms. We can't really define a chemical bond without saying it's what holds together chemicals. So you're using the definition, or you're using the word in the definition. Does that make sense? But we'll talk more about what types of chemical bonds there are, how those bonds are different from each other, how they're similar, how we differentiate them. Good. All right, the last part of that module 1, it's all about energy. And I will say, you will not have to do this energy concept in your unit test or in your exams. So the energy part of module 1, it's just real chem. These are the types of energy that module 1 introduced you to. Vital energy, functional energy, causal energy, and countable energy. I mentioned earlier that as scientists, we like to put things into boxes, so we develop these rules, we put these names to it, we draw these lines. This is one of the worst examples of that process I've ever seen. I cannot, for the life of me, differentiate between functional and causal. Because if energy has caused something to happen, it seems like it then had a function. It did something. So what is the difference? I don't know. And if vitality, the essence of being alive, is not a function or a cause, I don't know what it is. And if you can't count your energy, then I don't know what you're doing wrong. So I don't understand these. But again, luckily, these definitions of energy, they don't really show up on your unit test. You do need to know them, however, for your Module 1 checkpoint, or at least be able to give a guess at them. So what I want to take a chance to do right now is look at RealChem together. Now, how many of you have remembered that tip I gave on the first day about how to get to RealChem? Did you guys all bookmark it? It's a lot easier, right, than having to navigate to it every day. It is a pain, but it's kind of unavoidable. So what I want to do right now is actually take a second to look at this Module 1 checkpoint, except this is the unit checkpoint. So Unit 1, Module 1, basic concepts. Oh, that's my energy summary. All right, question 1. The goal is to figure out how to separate the sand and sugar. Once they're separated, we'll differentiate them. We'll figure out which is which. When we have them separated, here's what they'll look like. White sugar, white sand. Here is a phase diagram. It's not in atmosphere, it's in a different unit, kilobar. We've got a conversion between them. The question is, some of the white sand shown in the photograph at the beginning of this scenario is heated to a temperature of 600 degrees while keeping the pressure at 1 atmosphere, or about 1/1000th of a kilobar, which is about 1 bar. What is predicted by this phase diagram to be the stable phase of white sand at this condition? So zooming in on my phase diagram, temperature is 600. Here's 600. Pressure, 1 atmosphere, about 0.00101 kilobar. Where does 0.001 kilobar show up on my y-axis? At the bottom. That's basically the bottom of this graph. Here's 20 kilobar. Here's 0.001 kilobar. And here's 600 degrees Celsius. So, what phase would you expect this sand to be in? Alpha quartz or beta quartz? Not tridymite, not crystallite? I agree. Beta quartz. That was a lot of reading for not a lot of question. If I can give you any hint, it would be, don't feel like you need to read too much. If you get down to the question and know that you know how to answer it, answer it. And if you get to the question and realize you don't have enough information, then go back and find the information you need. That can save you a lot of time, not just in this class, but in academia in general. The pressure is plotted, again, the same thing, sorry. Starting with white sand at 1 atmosphere. It's been heated to 600 degrees C in a container that won't crack. A plunger pushes down on the container to put pressure on the hot white sand until the pressure is 10 kilobar. What is the phase change that occurs? So we said earlier that we were here at beta quartz. What is changing right now? Only pressure. So am I moving horizontally or vertically? Vertically at 600. What phase change will I see? Good. Started at beta quartz. We're moving over that phase line to alpha quartz. Which of the following statements is something that is the same about white sand and white sugar? Do sand and sugar smell alike? I don't know. Do they taste alike?
No.
You guys have eaten sand? Okay. They are in crystalline form. Do you know what crystalline means? Crystal clear. Rigid, and usually in a repeating pattern. But usually rigid is a good way of thinking about it. They dissolve in water. We wouldn't have many beaches if sand dissolved in water, would we? So we feel confident the similarity is crystalline. We're going to add water to the sand sugar mixture to separate the white sand from the white sugar. Why does dissolving in water work as a differentiating property for these two types of matter? They both dissolve in water. That wouldn't differentiate them. Sugar dissolves in water, but sand does not, or sand dissolves in water while sugar does not, or because dissolving in water is a physical difference. You're saying B or D? B. Sorry, I saw like the number 4, but also the ASLB. So B says white sugar dissolves in water while white sand does not. How is that different than the last option? Dissolving in water is a physical difference. Yeah, it's asking us, why is this a differentiating property? And it's true, yeah. White sugar does dissolve in water and sand does not, and that differentiates them. Is that not a physical difference between the two? Their solubility in water? So if you're anything like me, I'm actually torn on this one right now because I don't feel confident about a differentiating property. No, because I don't understand their wording. Do you guys agree? Their wording is actually a little off-putting here. This is something that you will experience this semester. You are going to run into this a lot, especially with real chem, but occasionally with the unit test and the midterm, where you feel confident about what the topic is. The only thing you don't feel confident on is how it's worded. And I'll be honest, it's not just this class. It's outside of this class. Not everybody is good at writing questions in a way that shows how well you understand something. So this is a challenge. I actually don't know. I don't know what to put. What would you guys put?
B.
Okay, you all feel pretty confident on B. I don't know. I don't know what it is. And they won't tell us the right answer. They'll just tell us that we didn't get it right. But then the second time you take this assignment, you're not likely to get the exact same questions. You might get something slightly different, which means you don't have to figure out the right answer the next time. You need to figure out the concept or how they're wording the concept, you know?
Will it tell us, like, so it won't ever just explain the answer?
Sometimes, not always. I think I did actually set it up so that it gives you hints as you go through, but it's not always that easy. All right, some examples of soap working to take dirt and dissolve it into water. Which of the models is modeling the in-between distance scale of the 3, not the largest and not the smallest? So here we've got a scale of soap being added to water and getting a soapy solution. Here we've got water molecules, soap molecules, and dirt molecules. And here we've got a zoom in of soap and water. Which of these shows the middle scale?
Model 2?
Do you guys agree? Which is the most zoomed in scale? Model 3, because you can see those atoms, only portions of them, but you can see them really well. I'm sorry, I'm realizing I'm not doing a good job placing this. And then, of course, the most zoomed out would be where you're dumping the water in. You've got your beakers and everything. Which of these distance measurements is the shortest distance scale measurement? The shortest distance scale measurement.
The one to the negative 12?
Yeah?
The smallest unit.
I heard to the negative 12 quite a bit. Can you justify it? There is another one that's less than 1. This one is also less than 1. If you, put them all on a scale like I had before, right? Each time you've got that negative exponent, keep pushing it to the left. If you think like Lizzie, then just write out all those zeros in front of it And to the negative 12 is going to have 11 zeros.
Just put them over and then it's like, well, this one's got like 2 extra, or in this case, like a lot of extra.
Eight
zeros.
extra zeros.
Yeah.
Good.
Sounds bigger.
Not trippy yet, but these numbers, they do get really big, they do get really small, and it is important to get familiar with those scales.
I have a silly question.
Yeah.
Is there any world where the exponent, let's say, is smaller, like it's negative 12 versus negative 11, but the whole number on the front is like, it's like a trick question where the whole number is like a 9 and the other number is like a 1 or a 2? If you have to actually calculate it more?
So not a bad question. One thing to remember though about scientific notation, technically the correct way to report a number is that it is at least 1.0 and smaller than 10. Actually, I'm going to put 10 there. So you cannot have a scientific notation that has 0 point blah, 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 times 10 to the whatever. And you can't have a scientific notation that says 252.683 times 10 to the negative whatever. So if done correctly, all of these have just one number in front. But your question is valid because sometimes we do diverge from that rule because it can be useful for us. So a wavelength of light, 252 times 10 to the negative 9th meters, 252 nanometers. This is in the UV range of light. I've broken the rule because 252 is much larger than 10. So if I were to write it accurately, 2.52 times 10 to the, you should have two options in your head. Times 10 to the negative 11 or times 10 to the negative 7. So how do we figure out which one is which? I'm moving my decimal place to the left, so I should make this negative exponent more negative. Times 10 to the negative 11 meters. Sometimes it is useful to break the rule of being between 1 and 10 because nobody wants to say that their wavelength of light is 2.52 times 10 to the negative 11th. And we'll talk about why, but we can say 252 nanometers instead. So it is used a lot. You'd have to pay attention. And so I think, like what you're saying, could I have 11 times 10 to the negative 12th versus 9 times 10 to the negative 11th? No, I think 9 times 10 to the negative 13th. And then ask which of these is a bigger number. I don't think RealChem's going to do that to you. And your unit test shouldn't because it diverges from what we should do with notation. Does that make sense? But which one is smaller?
Instead of negative 13.
Well, how about we put them both in the correct scale? Like, let's get the notation the same. So I can take 11 times 10 to the negative 12th, and I can write that as 1.1.
Just works.
Yeah, and when you get that many zeros, you've got to count it down and see.
That's not fun.
I can turn 11 into 1.1. I moved my decimal to the left, which means my exponent should become more negative. So now, from 10 to the negative 12, it's 10 to the negative 13th against 9 times 10 to the negative 13th. So which one is smaller? The first one, because 1 is smaller than 9. 9 is actually closer to 10. 10 to the negative, well, that doesn't make a lot of sense, does it? Did I move it the wrong way? I moved it to the left. It shouldn't go from negative 12. It should go, it shouldn't go to negative 13. Ah, I did it wrong.
I was gonna say before that first one,
You're right. You're 100% right. I screwed it up. I got my notation wrong. So let's backtrack and fix these two examples that I just screwed up on the board, shall we?
You can also ignore my question if we're going there.
Well, now that we've done it, I think it's worth being here. Okay, so what I said was moving to the left, make it more negative. And this is not correct. Take, for example, 1 million. Which way do you move the decimal? To the left. Does your exponent become more positive or more negative? Correct. So to the left, more positive. Take, for example, 0.001. Which way should I move my exponent? To the right. So should I make it more positive or more negative? More negative. So our rule of thumb, to the left, more positive. I'm putting 10 plus plus. Make it more positive. Move your decimal to the right, more negative. So I did screw up on the board twice. This should have been 2.52 times 10 to the negative 7 meters, not negative 11. See, it's worth going through it. And I screwed up down here because 11 times 10 to the negative 12 becomes 1.1 times 10 to the negative 11. So those of you that said times 10 to the negative 13th, you were right. My example was broken. Okay. Let's finish up these questions on here. The statement about washing clothes. What is the primary way to think about energy that you are using when you say that statement? Electricity makes the washing machine run. Vital, functional, causal, or countable? Someone say vital?
To me, I think functional.
I say causal.
Ah. Okay, yeah, so the washing machine runs. That's a function. Electricity makes it run. That's a cause. So, pretty sure this is energy is causal. Electricity causes the washing machine to run. The washing machine uses energy to wash your clothes. That's a function. But we're not talking about washing the clothes. We're talking about electricity running. When we hand wash clothes, we feel depleted of energy. Why is that? It's difficult to not be able to text on our cell phones. I'm surprised they didn't put in TikTok. Yeah, we have to use energy for our muscles to do the work of scrubbing the clothes. That energy, I think you could say, is vital. Or maybe it's functional. It's not the question, so it doesn't matter. Cooking over an open flame is common. Unrelated, the process of photosynthesis makes oxygen, which is essential for many life forms. Is oxygen gas, matter or non-matter, and how do you know? Okay, so good question. Someone's saying because it has mass and takes up space. One of them says it's made up of elements. Is it wrong that oxygen is made up of elements? That's true. Oxygen is made up of elements, but we defined matter as something that has mass and takes up space. All elements do, but things that are not elements also take up space and have mass. When the grill is working, it gets really hot and gives off heat. Food doesn't cook on the grill unless the propane burner is on. So, friend 1 says the food cannot cook without the fire being on. The heat must be an essential part of the process of propane burning. So the heat must be matter. The other friend says the heat is always there when propane is burning, but the heat isn't matter because it's not possible to contain heat in a box. You are next to speak, and you'll add to the conversation with the two friends based on your knowledge of chemistry. Which of the following replies is correct according to what we've learned so far?
Heat is matter because it participates in propane burning. Heat is not matter because it doesn't have mass and can't be sealed. Heat doesn't have any mass and it can't be contained in a volume, so it's not matter. Heat is matter because it takes up space. So, matter or non-matter? Non-matter. We know that much. We have two options we need to rule out. One of them said it doesn't have mass and it can't be sealed. The other said it doesn't have mass and it can't be contained in a volume. Then we've got heat is also not energy because it goes away after a while. And this one says heat is energy. That's why it goes away after a while. That energy dissipates. All right. What kind of change does this chemical equation represent? Propane and oxygen form carbon dioxide and water. Chemical, physical, or both? Or neither?
I would say chemical,
Why?
because we had two compounds and they switched into two other compounds.
If they've got different names, they're different things. I started with propane, but I don't have propane at the end, so I have a different chemical. I have a chemical change. Okay. Oh, finally. Which of the chemical equations represents a physical change? From a gas to a solid?
Solid to liquid. A.
So here I've got FeO2 and Fe2O3. So I think my chemical is changing. N2 and O2, NO2, I think my chemical is changing. CH2, C8H18, chemical is changing. So it must be A, but let's prove it. C6H12O6, that's a chemical formula. C6H12O6, that's a chemical formula. Same chemical formula. Same chemical. That's sugar. So this would be like if you're making a syrup and you're melting your sugar from a solid to a liquid. Okay. There we go. I guess the only thing left to do is see how we did on that one question. You guys remember the number? Yeah, me either. 7? No, it wasn't. It was much earlier. We got it right. So yep. So we were debating because dissolving in water is a physical difference, and that is true. And their answer was explaining it more, diving into it a little bit more. This is an issue I want you to be aware of when you're doing your checkpoints. Don't second guess yourself. Just recognize you may need to take that next attempt to give it another shot. Okay? Let's take a 5-minute break so you can get up and move around, get your blood flowing before we come back in for Module 2. While you're on your break, I'm going to put up our learning objectives for this unit.
Hi, I'm Megan. I was in another class when I switched over.
Great. I think I left some comments on your assignments, right?
Okay.
Which was like, I went through and did a lot of grading last night and just said,
Okay,
please
if it
submit
was-
if you haven't done
Okay, I had submitted all, I was hoping this wasn't gonna happen, but I had done
Oh.
up to unit, or
Yeah.
to unit 2,
it. Yeah.
but I can't, it's all done.
Yeah. Are you able to look at your inbox from when you got grades and just find the assignments that you got grades for and send me the grades over?
Okay, I can look on,
I had another student in a similar situation, and I wasn't actually sure how we do it. And then they messaged me last night and said, here are the assignments that I got grades for in my Outlook inbox. And then they gave me their instructor's name, but it's no good because that instructor doesn't have
any of mine.
the grade anymore.
I was like, that's the same email.
Or maybe like, I got full points on all of them, and you can just get of the assignments you got full points
I
on?
was honest, I think there was like a few that I was like,
Just redid them.
yeah, but
Like this wouldn't have been that hard, but easier.
I'm like,
And at least you're actually a little bit ahead, so now you're getting kind of a step back.
Yeah.
Better
I
than
mean,
the
it was
other way
a lot,
around.
honestly, it was so much, like, it was, when you were like, we're a little bit behind, I was like, I feel like the first, 2 classes were so fast that we didn't, I was like, this is the first day of class, and
Yeah.
we're all banned of like unit 1 basically. So.
Yeah, I know. Well, I try to go through a module a day, and I keep finding myself falling behind on that. I wish I could get through this in one day,
I mean, yeah.
but it just took me half of our class or more to finish the other module.
It's helpful.
But
so.
it is, and that's the other thing is, if I was just up here talking, it'd be one thing, but having the engagement is another. So I would rather take our time and make sure that we're understanding it, but I also want to stay on track and have time to finish early if possible. You know, not the whole semester, but so.
No, it's helpful. The conversation, the engagement is
Good.
like just reading real chem is one thing, but reading engagement is different. So.
Are you in the online section or in class? In person?
In person.
Okay.
Yeah, and then my chem lab, I'm still with the professor I was with. It's just on Tuesday evenings. So
Is it Heine?
no, Sledge. Yeah. So I'm on it at night with him.
I think we just hired him in
Yeah.
in his second semester.
So because he said that he was newer, but he was his classes between the 2 campuses was like I can't. And then when I saw yours open up, I was like,
Yeah.
So
Great.
Okay, I will look on in my inbox and
Yeah.
see which ones. If not, but like honestly, the extra practice, like because like you said, like I really want to learn it. I don't want to.
Yeah, but also this unit, it's just like some of it feels dumb.
Yeah.
Or like it should be easy, but they're wording it in such a way that it shouldn't be that hard.
Yeah, because the reason why I asked that question too was because when I had submitted one, I was like, I swear that was the right answer. And then I went back and screenshotted it, and I was like, submitted it again, and I'm like, why is this wrong?
Yeah.
So that makes sense.
Well, it's great to meet you, Megan.
Yeah.
Thanks for being here. I'm Minji.
Sir, yeah, I'm a little bit late today, and
It's okay. I'm doing attendance right now, actually.
oh yeah, I
So
just
you're all
want
good.
to ask this question.
You're perfect.
Thanks so much.
You're welcome.
It's for everything. Is it like
Yeah, Gabriel.
There's 2 dates in Real Chem and then Canvas. Are those dates for our class or is that for everybody?
Our class.
Just our class?
Yeah. So on Real Chem, on Friday, I think I shifted some assignments
Okay.
so that you guys wouldn't feel like you're on pace with the other sections, and that it feels more closer to our pace. Real Chem is our section. I was able to kind of tell it what rough schedule I wanted it to have.
So, alright. So I'm on track. Is what
Yeah,
you're
yeah.
saying. Okay.
Did you see my announcement last night?
Yeah, I read it like 2 seconds.
If you can like check through those lists I put, you should be good.
Okay, fine, thank you.
You're welcome. Carly? Great. Sorry, I'm just still trying to learn some names. Sadie? Sadie? Jordan, Sarah. Is Ellie here today? Hi, Ellie. Sorry, I think you were gone last week, right? So I didn't get to see your face with your name. Okay, good to have you. Ashley's not here. Ashley's here. Sorry, I meant to say Ashley is here. Thanks, Ashley. Yeah. I think you're the only Ashley that I have. Does that surprise you?
Really?
Yeah. I don't. Pretty sure. Both of our Cadens are here. Yeah.
Well, I thought you were here.
One C Caden, one K Caden.
We've had classes before where you're just chaos.
Really? Okay. Should I try to test myself on your names?
Yeah, sure.
Peter, Blake, Ryan, Caden, Ashley, Sadie, Ellie, Amir, Keon. I just said it, so I know it. Carly, Lizzie, Jordan, Caden, Berkeley. Berkeley, you're joining from online, right? The online class? You got into this class? Oh, I need to just put you on my list then. Good. Thank you. Alina, Megan, Mark, Brian, Gabriel, Jackson. You are joining from online. Laura, Jackson, Gerardo, Danila. You're on student association, is that right? And you're speaking today at the faculty senate meeting. I saw you on the agenda. I saw your name, and I was like, I recognize that name. And then I saw your student profile picture, and I was like, oh yeah, that looks like a professional headshot that student association gives. Awesome. Well, I'll see you this afternoon then. Edgar, Silver, Daulette, did I say that right? Awesome. Saint, Cole, Minji, and I'm not sure I have your name. Jacob. Awesome. I screwed up on a couple of them though, huh? Thank you guys. All right, let's get into Module 2. And let's be honest, unless we really fly through this, I don't know if we'll get through it. All right, our learning objectives here. We want to be able to convert units and terms. For instance, if I told you that I walk at 3 miles an hour, could you convert that into different units to tell me how many feet per second I'm walking? But more realistically, if I tell you that I have 6 megatons of coal, could you tell me how many grams of coal I have? We want to determine accuracy and precision. We want to recognize and use SI units. And we're going to work with sig figs, or significant figures, as well as uncertainty. Every measurement that you make has some uncertainty to it, and we want to agree on what counts as uncertain, even if that applies to being significant. How many of you guys like math? Wow, I was not expecting to see that many hands. Were you guys? I was surprised. Okay, yeah.
Sorry.
Yeah. But I mean, I think we had a lot of people come through that said well, we did have a lot of engineering majors. How many of you that raised your hand are also engineering majors? Oh, right. Okay, that checks out. And then the rest is pre-health? Yeah, sounds about right. I also like math, but I didn't know I liked math until I was in chemistry classes. So I only like math in the context of chemistry when I feel like it's serving a purpose. That's what I like about math. All right. Every measurement that you make should provide 3 pieces of information. Measurements have a magnitude. That's a fancy way for saying the number that you are reporting. If you weighed yourself on the scale this morning, that number is your magnitude. Measurements have a standard of comparison. That's a fancy way of saying it has a unit. If you weighed yourself and you found that your magnitude was 72, Lizzie is thinking with a specific unit, and you might be thinking with a different unit. Lizzie said, you need to see a doctor.
Yes.
And your doctor would say, you're healthy. 72 pounds, severely underweight. 72 kilograms, not a bad zone to be in, I think. I always forget. But if I remember right, 72 is like about 130 or something like that. Then measurements have an indicator of uncertainty. So let's say that I weighed myself this morning. And again, you guys saw that I don't really know what this number is. But let's say that I weighed myself and I weighed 72 kilograms. Great question. Am I a little over? Am I a little under? Or am I right at 72 kilograms? Then I weighed myself again at my doctor's office, and it came out to 72.1 kilograms. Am I more certain about my weight before or after my doctor's visit? I got another number. I got a number after 2, so I'm more certain that it is 72 and not 71.9, but I'm not 72. I'm 72.1. So my first measurement, I was actually uncertain about 2. Might be higher, might be lower, and it's just rounding. But now I'm uncertain about this 1. Might be higher, might be lower, probably rounding. Now, I'm not going to lob off that number. For instance, I'm not going to say, my scale said 72 kilograms, so I'll only report my weight as 70, because that's as confident as I can be. I am confident that I'm 72, but you recognize that 2 is a bit uncertain. And in the same way, when I weigh myself and say I'm 72.1, I'm not going to lob off the 1 and say I weigh 72, because I can say more confidently I'm 72.1, and you recognize the inherent uncertainty about that last digit. So this is the basis of all of our measurements, and we'll be focusing on measurements for this module. Let's dive into units, because units are an incredibly big part of scientific measurements. We're going to be dealing with SI units. That's actually the international system of units, but it comes from French, I think. So it's like, I don't know, anybody know French? Great. Said it better than I could. So we call it SI, International System. We're going to look at 2 types of units. We're going to look at base units. That's like saying grams, meters, things like that. And then we're going to look at things that I call prefixed units. Kilograms, milligrams, centimeters, kilometers. Those take your base unit and put it on a new scale. So let's look at some of our main types of measurements. Length. What's the base unit for length? Meters. And what is the abbreviation for that unit? M. Little m, by the way, not a capital M. I had an organic student the last couple of semesters whose font is writing in capital letters, but large and small so that you can tell like what is a capital and what is not. I would not recommend it. Since I can catch you early, I'm going to try to catch you early. In science, try to use normal font, which is, don't make this a capital M. I know it's kind of the same, but for other things, it does make a difference whether you're writing one unit or another. Now, I told you guys I'm learning Arabic, and Arabic has a very interesting script. The letters don't have capital and lowercase, but when they connect to other letters, they change their shape, and so it can change their meaning. Same thing with our capital and lowercase. They have different meanings. Take advantage of that. Recognize that. We measure mass a lot. What is our unit for mass? Oh, it is kilogram. I wouldn't have picked that. I'm sorry. I'm glad I had my notes. The SI base unit for mass is kilograms. What do you think I would have said? No. Grams. Because grams is a base unit and kilograms is a prefixed unit. I would not have picked a prefixed unit to be the representative. But they did. I'm glad you did your reading. Temperature. Good answers. Celsius makes a lot of sense. You guys that were raised in the US know that nobody else uses Fahrenheit. Celsius makes a lot of sense. But the international system is Kelvin, and that has unit capital K. It actually doesn't have degrees. So we have degrees C, degrees F, but we don't have degrees K. It's just K. Kelvin, come to my talk in November. I'm going to be talking a lot about the Kelvin scale. Kelvin is very important. And then the last thing that we can talk about here is time. And the unit there is seconds or small s. Now, where do these units get their basis? Remember, this is a standard of comparison. So, what is the reference that we are making a comparison to? Well, length is actually established by light. We say that 1 meter is the distance traveled by light in a vacuum over a specific amount of time. And it's like the smallest fraction you can think of because light moves very fast. So our standard of comparison for meter is light. Mass is by water. Although there are some extremely old, extremely sensitive, standardized weights, I believe, under the Louvre in France, that supposedly are the reference for mass. But it's not a good enough scale, so we use water predominantly. Temperature, being in Kelvin, this is set to nothing. We use absolute zero, the temperature at which electrons don't even have energy to move, to be our reference for temperature. Do you want to add to that? No, not really. Maybe, but even if we could, I don't know that we'd want to. We can get to millifractions or millikelvins, like very, very close to 0 Kelvin. But we actually need some energy. Supercomputers, quantum computing, requires electrons to hold information, and they need to have energy to do that. I don't have anything for time. And that very well could just be that we don't have a good answer. But my guess would be that it's based on light and or gravity. Because as you know, time changes depending on your gravitational experience. As you know. Okay. There are some other units that aren't as necessarily straightforward as these measurements. So your textbook describes these as derived units, units that require more than one measurement to make. One of these is volume, which is given little v. I guess sometimes it could be big V as well. And the SI basis for volume is cubic meters. Remember that volume is 3 measurements of length. That's why it's a derived unit. You need to measure 3 things. So you're going to measure length, 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 right? Length, width, height. Multiply them all together. And because it's based on length, it's going to be cubic meters. Density, often given capital D or rho, the Greek letter rho, which looks like a P. But the Greek letter rho can be used, I saw that a lot more in advanced classes and some physics classes. What would your units for density be? Not kilograms squared. Density is mass per volume. Mass, kilograms. Volume, cubic meters. Not meters squared, meters cubed. So recognize that this density equals mass per volume. A derived unit. You need to have more than one measurement in order to know the density measurement. Do you feel like there were measurements left out, units left out? Yeah, what comes to your mind? Yeah, volts or watts or amps, ohms, moles. That is an interesting unit. We're going to get into it more. Frequency, which is hertz, yeah. And we are going to talk about frequency of light. Hertz is named after a guy, and it's actually just per seconds. So hertz, Hz, is 1 over seconds or per inverse seconds. Good. Did we say watts? I think we said watts. Luminescence. Is that a unit though? Lumens, right?
I just got it in the writing. It's actually
A
a candela.
candle?
I don't know. I just read it in the reading.
You read the word candle?
Candela.
Oh. Lumens, I think, is a unit. Yeah, that would be a good one. I don't know if that's the SI unit, to be fair. Decibels for sound. This is good. What about radiation? Electromagnetic radiation actually has often 2 units that you can use. Hertz is one of them. And then the other is wavelength. So this is a frequency because it's something per something. It's a number per unit. That's a frequency. Like for instance, I make a pit stop 3 times per road trip. Road trip is my unit, 3 is my number. That's a frequency of stops I make on a road trip. Yeah. Wavelength for electromagnetic radiation instead measures length. So the base unit then would be meters. So electromagnetic radiation would have one of those 2 units. Actually. UV rays is electromagnetic radiation, is light. And so you could measure it with wavelength meter or frequency hertz per second. Either one. Cool. All right, good discussion. Now, in making these measurements, there are 2 things we want to consider. The first is precision, and the second is accuracy. Precision describes reproducibility. If I have a ruler or a meter stick and it only shows every foot, it doesn't show me inches, or it only shows every centimeter, it doesn't show me millimeters, then I've got a bit of an issue with my reproducibility because there may be times that I have to guess where the number is, where it falls, right? So reproducibility, precision, increases with graduations. It increases with markations. Increases with increasing marks or graduations. Try to draw an example. Which of these measuring sticks, notice there's no unit, has more precision? The one on the right, because it has more marks. If I were to measure a piece of paper using the one on the right, I could get to a closer number over and over again, reproducibly. But if I use the one on the left, I might be guessing. Now, especially if you and I try to measure the same thing and we both use this, we should reproduce the same number. But if you and I both use the one on the left, we very well may get different numbers. We won't reproduce the same number. So that idea of reproducibility gives us precision. Accuracy. Now, I think this will make a lot of sense to you. Accuracy is the proximity to the true value. Right. If it's accurate, it's true. Who decides what's true? If I want to measure my sheet of paper or Jordan's notebook, who decides what the accurate value of that length is? The paper decides. We give the paper that ability to say whether we have accuracy or not. Do you see the limitation here? If I want to know how accurate my scale is, I need to know that it's the true mass of my body compared to what? Right? Who decides what the true mass of my body is? I'm breathing out air all the time. I'm sweating out liquids. I'm putting in food. So the mass is constantly changing. How do we know that accuracy is really being held on to? This typically means comparing against other instruments. I might hop on my scale every day and it says 72 kilograms. Every day, 72 kilograms. And then I go to my doctor's office and it says 78 kilograms. Well, I want a second opinion. So I go to another doctor's office, 77 kilograms. Oh, so a third doctor's office, 78, another 79, another 77, another 78. I'm starting to get more reproducibility that's telling me my mass is somewhere between 77 and 79. So my scale is probably not accurate. It's not reporting the true value. But then again, 77 is not a good answer. 77 point what? 0.1000? How far can it go? Can I get down to the mass of every electron that's in my body? That would be accurate. So we're going to always fail to some extent at accuracy. And unless we keep having instruments to compare our measurements against, it'll be really hard to know whether we're accurate or not. I fully trust my scale telling me I weigh 72. I have no reason to doubt it until I go try myself on other instruments, right? All right. There is something different about counting objects and counting things than making a measurement. And that is exact numbers. They have no uncertainty. Things that you can count. So I don't have to be uncertain about how many students are in the room today because I can count them. There's no uncertainty there. It's precise and it's accurate. But if I wanted to try and make a measurement somehow, like taking the mass of this room and dividing it by the mass of an average student, well, then I would be making a measurement and I would have some uncertainty to it. And this we already talked about. Making a measurement always leads to uncertain numbers. This is the last digit in a measurement. "72", the 2 is uncertain. I measured that. I didn't count my mass. "72.1", the 1 is uncertain. I didn't measure that. I measured it. I didn't count it. So do you guys think you can come up with ideas of things that you count? People. Pills. If you're trying to... The volume in a container. Unless you're measuring it. You're using something to measure that volume, and you can't really count it. How many containers? How many objects you have? Feels a little non-scientific, right? Your digits, your fingers. I hope you're not feeling uncertain about how many fingers you have. That would be strange. So when we make a measurement, and then we take that measurement and we do calculations to it, we need to pay attention to the precision and the accuracy and how it propagates. So we're going to look at in our next class on Wednesday, we're going to look at the figures, the digits that are significant in our measurement, and how to make sure that we do calculations and limit the number in our calculations to maintain that precision and that accuracy. If you did an experiment and you came back to me and said, well, I was expecting to get this mass, and I did some math, and I got 97.324689137264091% yield. I got that much of what I thought I was going to get. I'd tell you, no way. There's no way you know that much precision, that close to your accuracy. Well, actually, I wouldn't know if you were accurate or not. But there's no way you get that much precision in our chemistry labs, right? maybe you could get 97.1% precision. You're always going to be limited. And so we're going to talk about how to look at your calculations to cut those limitations off. But don't be afraid of getting into it ahead of us and coming in with questions on Wednesday. All right? You guys have a good day. I'll see you for Wednesday's class. Take care.